Automotive Video Incorporated presents Real World Diagnostic Series.
Hi, I'm Pete Pilata, and thanks for choosing a PEG video training tape. Today we're going to cover port fuel injection systems, which is another classification of closed-loop fuel feedback systems that we discussed way back when with computer command control. Fundamentally, we're going to utilize the same principles we did in C3, only we're going to use a more sophisticated fuel metering system, that being port fuel injection, which is essentially one injector per cylinder. There's a lot of advantages to port fuel injection over, obviously, carburation and over electronic fuel injection or throttle body injection, as we looked at previously. Because we're using one injector per cylinder, the fuel metering capability of a PFI system is obviously much more efficient and precise than it was in TBI or C3. There's a few different terminologies that you'll be coming in contact with, and we'll discuss them. One, I said PFI, and PFI is really a generic term meaning port fuel injection. But there's more specific acronyms that we use. MPFI, which is multi-port fuel injection. SFI, which is sequential fuel injection. And TPI, which is tuned port injection. Now, essentially, these are all the same systems. There's only one major distinction between the few that I've mentioned. The MPFI or TPI, or tuned port fuel injection, is a double-fire simultaneous fuel metering system. What I mean by that is all the injectors are pulsed simultaneously once per crankshaft revolution. This is a double-fire fuel injection system. SFI, or sequential fuel injection, again, is essentially the same system with one distinction. That is that the injectors are pulsed one by one in the spark plug firing order. So if it was a V6 3.8 Buick, 165432 would be the spark plug firing order. That would also be the fuel injector firing order. So they're pulsed sequentially in spark plug firing order. And this is even a more precise way of metering fuel. These SFI systems, in order to start the pulsing sequence of the injectors, they will utilize a cam sensor signal. And this cam sensor signal will be the input signal to the electronic control module for starting the injector firing sequence. So again, this is one of the major distinctions between SFI and PFI. Some of the advantages over this system versus C3 and TBI, and remember now, what we're looking at here is an evolution of fuel metering technology. We talked about closed loop, and closed loop is the fundamental principle of an oxygen sensor, some type of fuel metering device, and an electronic control module. And in its embryonic stages, we started with a carburetor, progressed to the throttle body systems. Well, the port fuel systems is the most sophisticated system yet. And some of the advantages for port fuel versus the other systems are as follows. One, we don't need a thermostatic air cleaner, for example. In carbureted systems, as well as throttle body injection systems, we used a thermostatic air cleaner to improve fuel vaporization. Now, in throttle body injection, if you recall, the injector is placed directly above the intake manifold, meaning that it is at atmospheric pressure when it's delivering fuel. Now, the boiling point of fuel will decrease when pressure decreases, okay? So if we take the injector and put it inside the manifold, which is what we're doing on this particular system, okay, now we are at a negative pressure. So the boiling point of fuel is much lower than it is in a throttle body system. Consequently, we don't need a thermostatic air cleaner. We don't need an early fuel evaporation grid or a heat riser valve, because the fuel vaporization capabilities of the port fuel system are just excellent. Again, because we're inside the manifold when we're delivering fuel. And because of this, the fuel boils off very, very quickly and very efficiently. We don't need an oil splash shield on the intake manifold that we've used with older systems. Because remember now, the only thing that is being metered, if you will, or processed is air through the intake manifold or the plenum. There's no fuel being delivered through that particular component. So consequently, we don't need an oil splash shield. We used to use that to prevent overheating the intake manifold floor, okay, when we were metering fuel and air through a manifold. But again, we're just metering air through an intake plenum or manifold. Now, I talked about the different classifications of these multi-port fuel injection systems, and we talked about TPI, which is standing for tuned port injection. Essentially, it's the same metering system. They call it tuned port because the injector runners, okay, coming off the intake plenum are all of equal length and diameter. Okay, thus the classification is tuned port. This makes distribution to each cylinder perfectly equal, and Chevrolet has called this a TPI system. Even in throttle body injection, because we're still metering fuel and air, or distributing fuel and air through that manifold, we still have the problem of unequal air-fuel distribution per cylinder. If one cylinder is getting 85%, one cylinder can be getting 75%, one cylinder can be getting 100%, and so on. We still have the problems of fuel puddling in a manifold with a throttle body system. Okay, all these particular problems are eliminated with the advent of port fuel injection. Why don't we take a look under the hood and get an overview of the PFI system, look at certain components. And while we're on that subject, you'll notice that this is a 3800 3.8 V6 Generation 2 engine. Again, it's Generation 2, 3.8 being the Generation 1. This is a V6 Buick with a balance shaft, direct ignition system, electronically controlled EGR. So there's certain improvements on this particular engine that Buick has made over the course of that particular year. Very important when you're working on these systems is to identify what you're working on. And to do that very easily and quickly, look at the vehicle identification number and locate the 8th character of that number. It'll either be a number or a letter, and this will distinguish to you what the application is that you're working on. This is a 1988 Pontiac Bonneville. The 8th character of the VIN is a C, the letter C. And the letter C is the Buick 3800 V6. And that's what we're working with here. So it's Pontiac, but it's a Buick engine, okay, which is obviously nothing new to any of us at this point, okay? Some other applications that we're using PFI system on, a 1.8 liter turbocharged Pontiac engine uses the port fuel injection system. Now, let's make a distinction, though, between the engine I just mentioned and the engine that we're looking at here. The 1.8 liter turbo Pontiac uses port fuel injection, only it uses a speed density system for measuring airflow. And the engine that we're going to look at here is the 3800 V6 uses a mass airflow way of measuring the airflow through the engine. Basically, there's a distinction between the two. The speed density is, you can think of it as an indirect way of measuring airflow. Based on certain calculations, such as MAP, volumetric efficiency, EGR flow, engine variables, and certain things like this, we will calculate what the airflow through the engine actually is. On mass airflow, such as this particular system, we're going to measure the airflow directly, okay? Now, one thing here is to point out, on a speed density system, if we develop an air leak in the system, the increase in manifold pressure, okay, will signal the ECM to increase injector pulse width, and in most cases we'll see that the RPM of the engine will increase if you would disconnect the vacuum hose on a speed density system. On a mass airflow sensor system, because if we develop an air leak beyond the airflow sensor, obviously we can't measure it now. And we have to rely solely on the oxygen sensor to pick up that extra oxygen. Now remember though, if we're an open loop or if we're starting the car, you will find that you'll have more difficulty in starting a mass airflow sensor system if it's got a large vacuum leak. And a speed density system will probably start right up. So there's a big difference there between the two measuring ways that we're doing this. As a matter of fact, on certain 2.8 Chevrolet engines, they actually went from mass airflow in 1985, 6, and 7 and went back to a speed density system in 1988. Speed density is probably the best way of doing it, and I guess it took them a couple of years to find that out. So there's a couple distinctions there that you can make. Let's look at some of the components underneath the hood on this mass airflow system. And right here is the mass airflow sensor itself. Okay. This is your throttle body assembly, your mass airflow sensor. And to the left of the mass airflow sensor is your throttle position sensor. To the right of your throttle body is the idle air control valve. This is going to bypass air below the surface of the throttle plates for idle speed control. To the right of that is your EGR valve, which I had mentioned earlier on this particular system is an entirely electronically controlled valve. There's no vacuum hoses going to it. There's 3 separate orifices and solenoids inside this valve that the ECM will pulse up and down based on throttle position and load. Okay. If we swing around here a little bit, let's look at the fuel rail and the injectors. And here we have your fuel feed line going into your fuel rail assembly. The fuel rail assembly kind of just hugs the intake plenum, which is this section right here. And we will see right here, this is a fuel pressure tap. This is where we're going to take our fuel pressure measurements, which we will see a little bit later, are the most critical things that we need to do in this particular system. Here's our fuel pressure regulator, which is going to help us regulate the amount of pressure at the injector tip. Right here is your fuel return line, which we're going to pump the excess fuel back to the fuel tank, fuel that we're not using. And of course right here are your individual injectors, 1 per cylinder. Okay, 1 per cylinder here. Another benefit to this system, and I talked about some of the benefits, we all know the entire development of these closed-loop systems was because of fuel economy and exhaust emissions. And beginning with the C3 system, it did a pretty good job of fuel economy and controlling the emissions at the tailpipe. As the technology increases and as the sophistication of these systems increases, we can get even more precise fuel economy and exhaust emissions. Now, in addition to those two things, we're actually increasing performance too. And I'm sure you've noticed if you've driven these late model cars that the performance is really coming back underneath the hood. In the early 70s, we took a basic engine and just bombarded it with retrofit type emission equipment, which defeated the purpose of fuel economy because it loaded the engine down and robbed it of horsepower. Now what we're doing is, and you can see how clean this engine is, it's really void of vacuum hoses and excess parts. Because now what we're doing is by precisely metering the fuel, we are getting the fuel economy emissions that we want, and we're also increasing performance. The throttle response on these systems is absolutely excellent because we're delivering the fuel right at the base of the intake valve. So it doesn't have that manifold to travel through, as I said before. And in addition, with the ram tuning effect we're getting from these manifolds, we're increasing the torque output of these engines lower in the engine's power band. And what this enables us to do is use taller rear axle gears, or if it's a front drive, final drive gears. And this optimizes fuel economy. Because now when we're driving down the road at 60 miles an hour, obviously if we have very, very short final drive gears, the engine's really going to be screaming, doing like 60 miles an hour. You might be turning 2,500 plus RPM. With increased torque output and the ability to use taller gears, now you can be doing 60 miles an hour, and in fourth gear overdrive, you could be turning like 1,800 RPM. So again, performance and economy, the two are really working hand in hand today. So the evolution has been a great benefit to us. And because of that evolution, because the technology continues to move forward, so does our training, and that's what we're about to do. All right, let's take a look at the fuel delivery system. And we're going to start right here at the fuel tank. Fuel is filtered through this in-tank inlet filter. Okay, it's a 50 micron filter. It'll filter particles within 50 millionths of an inch. Okay, it is then pumped through the in-tank fuel pump into the fuel feed line. Okay? It comes up here through an inline 10-micron fuel filter. Okay? And by the way, when you're doing a tune-up, don't forget that there's a filter on the system. It's located, in most cases, in the rear of the vehicle near the fuel tank. It's a 10-micron filter. Okay? Particles within 10 millionths of an inch. So don't forget that's there. Okay? When you're doing a tune-up. The fuel, this is, by the way, this would be a steel line. It was going to come up through a rubber flexible hose, okay, as it makes its way to the fuel rail, okay. Once it enters the rail, it will go through the rail and be metered, or the pressure of the fuel will be metered through the fuel pressure regulator. Okay, the regulator is connected to a manifold vacuum signal, and this will meter the fuel pressure, which is ultimately delivered to the fuel injectors. Okay? Now, the fuel that we're not using, we are going to deliver back to the tank through the fuel return line. And depending on the opening of the fuel pressure regulator, this will dictate how much fuel we're going to deliver back to the tank. Okay? That fuel will go through the fuel return line through a flex hose, okay, and be dumped back to the tank. It's almost a closed system, as you can see here. It begins and it goes in a complete circle. Now, one of the advantages of this fuel metering system is simply this. We can eliminate the potential for vapor lock because we are always delivering cold fuel to the engine. The fuel that we're not using is pumped back into the return line, and then again we're getting a nice fresh supply of recycled fuel, if you will, to the rail. So we're eliminating the potential for vapor lock, which is a very common problem in carbureted systems. Okay, let's look at some of the components that we discussed briefly on the chart, beginning with the in-tank fuel filter. Okay, again, we said this was a 50-micron filter, and this will initially filter the fuel that's delivered to the pump. Again, don't eliminate this, or don't forget this. It can create some drivability problems, obviously, if it's clogged up. So always keep that in the back of your mind for some lean running or fuel pressure problems. In addition to the inlet fuel filter inside the tank, we talked about the inline fuel filter, which is this metal can variety, 10-micron filter. Okay, and again, tune up, don't forget to change the fuel filter. Okay, a lot of guys forget this because, again, it's to the rear of the car and underneath and you can't see it. Okay, it's expensive. It's between $18 and $20, and your customer will probably more or less complain when he sees that on his tune-up bill, but hey, this is an integral part of a tune-up, so don't forget the inline fuel filter. Okay? Now, here's your fuel pump assembly, and the metal casing of a fuel pump is contained within a rubber isolation sleeve, and this is to eliminate the high-pitched humming noise of the fuel pump. The fuel pump will turn at a precisely 3,500 RPM. It's capable of delivering more fuel than the engine could ever possibly consume, even at wide open throttle. And deadhead pressure on this pump is good for about 85 PSI. When I was in high school in biology class, I was always the guy who liked to dissect the frogs, so I decided to dissect one of these fuel pumps. And what I did was, okay, by taking the top half of the fuel pump off, I want to show you one of the most important components inside this fuel pump, and that is the check valve. It's a one-way check valve, and what this does is it maintains fuel rail pressure when the engine's shut down. Okay, obviously the valve will open up in one direction as fuel flows out of the pump, and when you shut the vehicle down, the spring-loaded check valve will shut, preventing fuel bleed back to the tank. This maintains a residual rail pressure for quick starting. Okay, if you have a long cranking complaint, one of the possibilities of that could be a stuck check valve in the fuel pump. And a little later we'll show you exactly how to diagnose this, but again, right now it is there, so be aware of that. Okay, the fuel pump is a DC motor, okay. The armature is going to drive the roller vane assembly, okay, which is your high pressure pump, and connected to the end of the armature will be an impeller, and this will be a vapor separator and a precharger for the fuel pump. Okay, so vapor lock again is really not a problem with this kind of fuel delivery system. high pressure, high flow fuel pump. The fuel pump is attached to the fuel sending unit and the feed line by means of a fuel pressure pulsator. Okay, this assembly right here. The fuel pump is attached on one end and the other end is going to your fuel feed line. This assembly is there to isolate hydraulic pressure pulsations to really minimize the mechanical noises of fuel delivery. Okay, let's take a look at the fuel pressure regulator. And this device is going to, again, regulate the amount of pressure, okay, where the fuel is coming, fuel delivery to the injector. In a TBI system, the pressure drop in the fuel system is very small because we only have either one or two injectors. So when they open, the pressure drop is relatively small. In addition to this, the injector, as I said previously, is above the intake manifold, so fuel is always being delivered at atmospheric pressure. On a port fuel system car, the injectors are inside the manifold, so fuel is being delivered in the absence of pressure. Okay, with the throttle plate closed, fuel is being delivered at a zero pressure situation, or very, very close to it. At wide open throttle, okay, now fuel is being delivered at atmospheric pressure inside the manifold. So we're going to have to regulate the amount of fuel pressure up and down that scale. In addition to that, the fuel pressure specifications for PFI are much greater than they are for TBI because we're pulsing either 4, 6, or 8 injectors simultaneously. Consequently, the pressure drop is much greater. So to keep fuel flow consistent, we need to increase the fuel delivery pressure. Now, the pressure delivery specifications on a PFI are between 28 psi at an idle, or a closed throttle, to about 42 psi at wide open throttle. And these pressure differences are regulated by this component here, the fuel pressure regulator. Now, this is a spring-loaded diaphragm type valve, okay? And let's take a look at where the fuel will enter the regulator. Okay, this regulator is attached directly to the fuel rail, okay? And fuel is going to enter the regulator, okay? And we have a spring-loaded diaphragm here. Okay, the orange color here represents manifold vacuum. Okay, this is going to be connected to a manifold vacuum source, this spring-loaded diaphragm. As fuel enters the pressure regulator, the pressure of the fuel is going to push up on this diaphragm, and the manifold vacuum is going to lift up this diaphragm. Consequently, it is going to be opening an orifice right where my pointer's at to the fuel return line. And the greater this orifice is open, obviously, the lower the fuel pressure is. Okay? And we are returning fuel to the tank. Fuel is represented on this chart by the red color. And if you follow my pointer, the orifice is open, and now we are returning a portion of that delivered fuel back to the tank. Okay? Now, under wide open throttle conditions, when manifold vacuum is at zero, okay, so we have an absence of vacuum here. Obviously, we have a pressure here now. The spring will force the diaphragm down, closing this orifice completely. Now, the fuel will hit a closed orifice, or a immovable force, if you will. We will not return any fuel to the tank, and now we'll be delivering fuel to the injectors at maximum pressure, which in this particular system is roughly about 42 psi. Now, to test this component very simply, and we'll do this, if you have your fuel pressure gauge detached, okay, when the engine is idling, you will have, again, between 28 and 30 psi. If you would just pull this vacuum hose off, you would close this orifice, you would shut off the fuel flow in the return line and maximize fuel pressure, you should immediately see that reflected on your fuel pressure gauge to about 42 psi. And that's going to indicate, obviously, that the fuel pressure regulator is working properly. We can also test this component, again, with a vacuum pump if we choose to do that, to see what the different pressures would be at the different inches of mercury levels, okay, that would create with the pump. But essentially, that's the way it works. It actually changes the orifice opening from the inlet to the return line. Okay, let's take a look at the fuel injector and its location. Okay, the fuel injector, okay, which is connected directly to the fuel rail, okay, and mounted inside the intake manifold. okay, or mounted to the intake manifold. The injector nozzle is obviously inside the manifold, okay, will deliver fuel in a 25-degree conical spray pattern right to the base of the intake valve, okay, right to the base of the intake valve. Now, if you notice, the injector is going to have a rubber O-ring where it connects to the intake manifold or where it mounts in the intake manifold, and a rubber O-ring where it mounts into the fuel rail. Now, obviously, these O-rings are very important for fuel leakage here, where it mounts to the rail, and for air leakage here, where it mounts to the manifold. When you're replacing injectors, okay, it's a very good idea to coat the O-ring with some ATF so you can easily, okay, insert the injector into its location and not disturb the O-ring seal. Again, any leak here is going to create a lean running condition because now you're going to be delivering additional air to that particular cylinder. Okay? These injectors are controlled by the ECM. Okay, the ECM is going to control the ground side of the injector circuit. We're going to supply 12 volts to the injector through an ignition feed, and the ECM will be responsible for completing that circuit to ground to energize the injector. Anytime it energizes the injector, it'll lift the pintle off its seat and deliver the fuel, which is under pressure, to the base of the intake valve. The injector is located about 70 millimeters away from the base of the valve. Okay? And again, this gives us precise fuel metering and excellent throttle response. On some specific port fuel injection system applications, we're going to incorporate one additional fuel injector in addition to the 6 or 8 injectors that we already have on the engine. This is a cold start injector or a cold start valve. This is only used on these specific engine applications, a 2.8 Chevrolet-built Generation 1 V6, Chevrolet-built 5-liter V8 TPI, and the Chevrolet-built 5.7 V8 TPI. The cold start injector is used to provide additional fuel to a cold engine on initial startup. On these particular applications, the normal injectors are not pulsed long enough to provide that cold enrichment fuel, so thus the need for an additional injector was required. The cold start injector is connected right from the fuel rail. There's a pipe from the fuel rail that goes right to the cold start injector. It is only activated in the cranking mode, and it is not, I repeat, it is not ECM controlled. It is provided voltage right off the starter solenoid through a purple wire to the 3-amp crank fuse. This voltage goes to the thermal time switch, okay? And the thermal time switch is screwed into a coolant passage, so it is submersed in the engine coolant. The ground side of this circuit, okay, goes right to one side of the cold start injector, and in a parallel circuit we also have 12 volts going to the other side of the injector. Now here's the way the circuit works. The thermal time switch will ultimately control the ground path to the cold start injector. Now, the thermal time switch is deactivated deactivated at 95 degrees Fahrenheit or 35 degrees Celsius. So at that specific coolant temperature, this bimetal switch will remain opened and this will not be energized. Okay? Below 95 degrees Fahrenheit, this bimetal switch will be closed, completing this circuit to ground. So as we crank the vehicle, we are applying 13 volts to one side of the injector, and the ground path is completed through the thermal time switch. Now, in the thermal time switch, there's also a heating element. And what this heating element is there for is this. It will provide a maximum on time of 8 seconds for the cold start injector. Now, here's how this works. The bimetal switch is directly affected by the coolant temperature. The higher the coolant temperature, the shorter duration that the switch will remain closed. Now, at minus 20 degrees Celsius or minus 4 degrees Fahrenheit, what happens is, because the coolant is so cold, this bimetal switch would remain closed for a long period of time. Well, by applying 12 volts to this heating element, this will open the bimetal switch after 8 seconds to prevent too much fuel from being delivered on a cold start crank. So again, at minus 20 degrees Celsius, here's would be the scenario. Okay, because the coolant temperature would be so cold, okay, the bimetal switch, of course, would be closed. Now, without the heating element, this bimetal switch would be closed for an extended period of time, which could provide too much fuel for cold start enrichment. So with the heating element, once we hit an 8-second interval, the switch will open and it will de-energize the cold start injector. Now, as coolant temperature rises, cold start injector on time decreases. So this cold start injector will remain on for a maximum of 8 seconds, provided by the heating element, at minus 20 degrees Celsius. At 35 degrees Celsius, the on time of this injector is going to be down to 1 second. Okay, the reaction between the bimetal switch and the coolant temperature. As coolant temperature rises, the thermal time switch or the cold start injector on time decreases. Okay, based on what we've just discussed with the cold start injector, let's look at some drivability symptoms that we may encounter. If we have a customer complaint saying that car starts fine warm, but it's very hard starting cold, and as a matter of fact, the colder it gets, the harder it is to start. Okay, that is a very good likelihood that we have a problem in the cold start circuit. Okay, to test the cold start injector, remember now, this is not ECM controlled. Okay, it is not ECM controlled. So what we're going to do is we're going to hook our fuel pressure gauge up, and as long as the temperature of the engine is below 95 degrees Fahrenheit, that circuit should be energized in the crank mode. We hook our fuel pressure gauge up, and what we're going to do is we're going to disconnect our 4-wire distributor connector. This will prevent a tach signal from reaching the ECM, and consequently it will not pulse the other injectors. Now, when you crank the vehicle, your pressure reading on the gauge should drop as the cold start injector opens. Okay, so below 95 degrees Fahrenheit, with the 4-wire distributor connector disconnected, while you're cranking the engine, you should see a pressure drop of between 3 and 4 psi as the cold start injector begins to open. If there is not a pressure drop, well, it's very likely that the cold start injector is not operating, and this is your cold starting problem. On another drivability symptom note, perhaps the complaint is poor fuel economy or possibly black smoke. Or again, possibly a hard start. Now let's look at this. If the cold start injector is leaking, okay, so when we de-energize, of course, the pintle should close and shut off the fuel. If the cold start injector is leaking, a few things are going to happen here. Obviously, when the vehicle is running, it's going to be getting more fuel than it should. And again, depending on the severity of the injector problem, it could create a black smoke problem, possibly a hydrogen sulfide odor out of the exhaust from the catalytic converter. Possibly a code 45, exhaust indication rich, okay, and a check engine light. Now, on the other side, if the injector is leaking, we talked about residual fuel pressure in the rail. So when you shut the car down, all the injectors should be off, and the pintle should be closed. If the cold start injector is leaking, okay, the residual rail pressure will let fuel drip into the intake manifold just while the car's sitting there. Now, upon restarting, if enough fuel has dripped in there, obviously the engine's going to be flooded out and will either be very, very difficult to start or potentially not start at all. So again, the cold start valve can definitely be a potential problem, okay, with hard starting conditions or rich running conditions as well. So let's look into that again on 2.8 Generation 1 V6s and the 5 and 5.7 liter Chevrolet V8s. While we're on the subject of the cold start valve, if you notice I talked about the applications that use the cold start valve. Well, I guess you're probably asking yourself, why don't the other applications use it, such as this Pontiac Bonneville? Well, basically the cold start valve is used on those systems that the ECM will not pulse the injectors on long enough during a cranking mode to deliver enough fuel to the engine for a cold start. These particular applications, such as this Buick engine in this Pontiac, is programmed to pulse the injectors on long enough, so it doesn't need an additional injector to supply it with cold cranking enrichment fuel. Based on coolant temperature, throttle position, okay, the ECM is going to decide what the injector pulse width should be. For example, on a very, very cold engine, such as like 0 degrees Fahrenheit, we would pulse the injectors the equivalent of a 1-to-1 air-fuel ratio. On a warm engine, okay, or let me give you this example, if the engine was flooded, okay, in order to clear a flooded motor, if we would put the accelerator pedal down, okay, all the way, okay, increase throttle position to over 80%, okay, while cranking the motor, the ECM would now pulse the injectors the equivalent of a 20-to-1 air-fuel ratio. So it would pulse it very, very rich on one end for a cold engine. If the engine would become flooded and you would, press the accelerator to the floor, the increase in throttle position at a specified RPM, in this case cranking RPM, which would be between 2 and 250, say, RPM, tells the ECM, pulse the injectors very, very lean so we can clear out this flooded condition. So basically, cold start injector versus no cold start injector, it's basically on the way the ECM is programmed and designed for the particular application. Okay, let's take a look at the fuel pump electrical circuit as it applies to Chevrolet applications and non-Chevrolet applications, because there is one major distinction, and I'll make that a little bit later. Basically, we have battery voltage applied to an oil pressure switch. When you start the vehicle and oil pressure is at least 5 psi, the switch contacts will close and it will apply 12 volts right to the fuel pump. Now, in addition to the oil pressure switch, which really is a redundant switch, we're going to use a fuel pump relay. And this is going to give us the ability to pre-pressurize, if you will, the fuel rail. As soon as we turn the key on, the ECM for 2 seconds will energize the fuel pump relay. Through a 12-volt fuel pump relay drive, we apply that voltage to terminal C of this fuel pump relay, and terminal B of the relay is grounded. When we energize this relay coil, okay, we will close this particular switch, and now we are going to apply 12 volts through the closed switch right to the fuel pump. Now, what will happen is the fuel pump will run for 2 seconds when we turn the key on, and then it will shut off. The fuel pump will not continue to run until the ECM receives a distributor reference signal. Now, let's take a look at a couple different things here. Drivability symptom is long crank times. In other words, the vehicle will start, and once it starts, it runs fine, but it takes a long time to get the vehicle started. A very, very good possibility the fuel pump relay is at fault here. Again, we have basically 2 switches that control the fuel pump, so really it's a redundant type situation here. We could do without one or the other. If the fuel pump relay would fail, and when we turned the key on, we didn't pre-pressurize the rail, if you will, we would solely depend on the oil pressure switch to close to turn on the fuel pump. Now, the reason long crank time would be experienced is because we would wait, or we'd have to wait till oil pressure built up to enough of a level to close these switch contacts. Okay, so the car would start, it would just take a little longer, so your crank times would be extended. So extended crank times very, very typically is a bad fuel pump relay. Now, I want to look at something else here. Chevrolet uses, to help you diagnose a bad fuel pump relay, a code 54. Now, how they determine this is this. They run the fuel pump voltage in a parallel circuit back to the ECM, and it's called the fuel pump signal or the voltage monitor signal. When you turn the key on, okay, key on, engine off, as soon as you turn the key on, the ECM expects to see 12 volts at the fuel pump signal line. Okay, if it does not see that, okay, then what it's going to do is it's going to condemn the fuel pump relay, because obviously there must be a break somewhere between terminal A to the relay and the fuel pump signal, or perhaps this switch isn't closing, or in any case there's a defect somewhere in the fuel pump relay circuit. If it doesn't see the voltage there for 2 seconds when we turn the key on, it will set a code 54. Okay, and again, this will help you diagnose an extended crank time. Now, also connected to your fuel pump relay is a fuel pump test lead. On Chevrolets, this will go to terminal G of your assembly line communications link. Now, the way this is used is simply this. If we apply 12 volts to this terminal G, okay, if you follow my pointer here, 12 volts will go through these closed switch contacts inside the relay and apply directly to the fuel pump. Now, when the fuel pump is energized, okay, this switch will close, but the terminal G switch will open. So terminal G is only used to pressurize the rail, okay, without or it's bypassing the ECM is exactly what it's doing. You're going to manually apply 12 volts to terminal G, and that will turn on the fuel pump, okay? Now, if you apply 12 volts to G and the fuel pump's not running, it's very, very possible that the fuel pump relay is defective, and this switch is open inside the relay, okay? Now, this is going to help us do a fuel injector balance test. We can pressurize the rail rather than turning the key off and on. We can just apply 12 volts to terminal G to help pressurize the rail. Okay, we looked at the fuel pump electrical circuit for Chevrolet applications, and we said that Chevrolet incorporates diagnostics for that particular circuit through a code 54. Now, what you see here is a fuel pump electrical schematic for non-Chevrolet applications. Now, this does not incorporate self-diagnostics for a malfunction in the circuit. However, remember we talked about terminal G for Chevrolet, and we use that to pre-pressurize the fuel rail? Okay, on these non-Chevy applications, we can use terminal G to do that, and we can also use terminal G as diagnostics to see if the relay is any good or not. So even though we're not, they don't give us self-diagnostics with the non-Chevrolet, we can self-diagnose it ourselves through terminal G, and we'll look at that in a minute. Okay, let's look at the basic schematic, and fundamentally, it's the same as the Chevrolet. We've got 12 volts going through a oil pressure switch, which in many cases is a dual switch. It's used as the oil pressure gauge switch and the oil pressure switch for the fuel pump. Okay, so 12 volts through the normally open with the engine not running oil pressure switch. Okay, when the engine starts and we reach at least 5 psi oil pressure, the switch contacts close, and we apply 12 volts through the fuel pump fuse to the fuel pump. Okay? Now, let's look at our relay. When we turn the key on, okay, and the ECM gets an ignition feed signal, it will apply 12 volts through the green-white wire on your 12-volt relay drive to terminal A of the relay. Terminal C of the relay coil is grounded. Okay? This will energize the relay coil. The magnetic field will create, and it'll make this switch close right here. Now 12 volts will go through the fuel pump relay, right through the fuse onto the fuel pump. Now, if you notice, terminal G in this non-Chevy application is run in parallel after the relay. So look what happens. We can use this in a twofold purpose. If we want to do an injector balance test and pressurize the rail with a jumper wire and 12 volts, we can apply 12 volts to here, and we will run the fuel pump. If we want to diagnose the fuel pump relay circuit, well, all we need to do is put a test light in terminal G to ground. When we turn the key on, these switch contacts will close. We will put 12 volts onto terminal G. Our light should light for 2 seconds and then turn off if the fuel pump relay is good. So we can diagnose a fuel pump relay circuit in a non-Chevy application with a test light through terminal G. Now, a note here. On those applications that do not use a test terminal G in the ALCL, you will find an underhood connector, like we will on this car, and we'll take a look at that. Okay, based on the electrical schematic that we just looked at for the fuel pump circuit on a non-Chevrolet engine, let's look at the diagnosis of the fuel pump relay using a test light. Your fuel pump test connector is right by the battery on the passenger side of this 88 Pontiac Bonneville. If I ground my test light and I plug my test light probe into the test connector. I'm using a jumper wire here that's plugged into the test connector. Okay? When I turn the key on, the test light should light for 2 seconds, indicating the fuel pump relay circuit is operational. Let's turn the key on. The light lit for 2 seconds and then turned off, indicating the ECM is controlling the fuel pump electrical circuit properly. When you turn the key off and turn it back on very, very quickly, the ECM will not energize the fuel pump relay, unless you have the key off for a minimum of 10 seconds. Idle speed. We're going to use an idle air control valve in the throttle body assembly. And as the chart shows, okay, it's going to be screwed in directly to the throttle body, and it's going to control an idle air bypass channel. Okay, what this valve consists of is basically a pintle, okay, and this pintle will move in and out of its passage to either close off the air bypass or open it up. Now the ECM controls this, if you're looking at it on your scan tool, in counts or steps, and your scan tool will show 0 to 255. 0 would be the indication that this valve is fully extended into the air passageway. 255 would mean that it is fully retracted, delivering maximum air bypass. Now, when we close this off, or we have 0 counts and it's sealing off the air bypass, the only airflow we have through the engine is what is between the throttle plate and, of course, the induction system, okay? So all airflow is directed through the throttle plate. As this starts to retract in its steps, okay, we are now channeling a predetermined amount of air through this bypass channel below the throttle plates to increase idle speed. Now, a code 35 will set if the idle speed, the curb idle speed, is 100 RPM above or below what is calibrated in the prom. Okay, so if this is out of range 100 RPM high or low, it'll set a code 35. This condition would have to exist for approximately 45 to 60 seconds to set a code 35. Now, this idle air control valve comes in 3 different styles or 3 different tips. We have a single taper tip, a dual taper tip, and a blunt tip. And basically what you need to understand is that you should replace the one that you're removing with the proper tip. Don't replace a single taper with a blunt and so on and so forth. So make sure you have, take a good look at the valve and make sure you're replacing it with one of the exact same origin. If you viewed our electronic fuel injection tape, you'll notice that the similarities here, basically the valve is the same valve, okay? Not to mention the fact that, as a matter of fact, this drawing, if the way it's pictured here is a throttle body. If you want to turn it sideways, it could be a port induction system. The theory, the fundamentals of this circuit are entirely the same as they are for throttle body injection. Okay. One thing I want to point out, and a few guys get in trouble here, when you have your scan tool plugged in on a port fuel injected system, okay, most scan tools will go right to the ALCL mode or the 20 KO mode. This tells the ECM to command a 1,000 RPM idle speed. Now, don't try to set idle, okay, as we'll see a little bit later, with your scan tool plugged in. Like I said, it pre-programs that idle air control at 1,000 RPM. And I've seen guys try to repair cars with high idle problems, not realizing that they have their scan tool plugged in the entire time. So that's a very important thing to remember. When your scan tool is plugged in, it'll automatically idle at 1,000 RPM, okay? And as far as the blunt tip and dual taper tip configurations, again, the only difference actually between the throttle body and the port fuel injected systems will be the thread configuration. For the most part, they are interchangeable devices, okay? And one thing you can do a number of things to check these, and one is very simple. If you create a vacuum leak in the vehicle, the ECM should respond by retracting, okay, the IAC valve to its, full, closing. And what you'll probably see on your scan tool is a 0 indication as far as steps or counts. And if you see that on your scan tool, it's a very good indication that you have a vacuum leak somewhere under the hood, because ECM is trying to compensate by lowering the idle or reducing this air bypass channel. So that's one way of checking your idle air control valve. Okay, let's look at our next chart here. And we've pretty much covered some of the fuel system components that we're going to be looking at in this particular system. This chart is labeled parameters, and we're going to be talking about sensed parameters and controlled parameters. Okay? In previous tapes, we dissected each sensor one by one, so we pretty much have a good idea of how the sensor and its electrical circuit work. We're going to just touch on a few things here to see some of the similarities and some of the differences on this particular system. For example, let's talk about the air conditioner compressor, okay, as a sensed parameter. Is the compressor on or is the compressor off? Well, whether it's on or off, this sense parameter will in effect tell the ECM to control the idle speed through the idle air control valve. For example, when we turn the AC compressor on, okay, that signal will go to the ECM, and with a delay of about 0.4 of a second, the ECM now will say, okay, increase the idle speed, okay, to compensate for the additional load. And it'll do that using the idle air control valve that we just looked at. So it would sense the air conditioner compressor on or off and control the idle speed as a result. Okay? Let's take a look at the coolant temperature. We're sensing coolant temperature to control a variety of parameters on the control side. Coolant temperature is going to help us control idle speed. For example, if the coolant temperature is very, very high, and if you remember back on our previous tapes, the resistance of the sensor would be very, very low, so the signal voltage of the ECM would be very low, indicating a hot engine. To compensate for the hot engine, the ECM would increase idle speed, turn the water pump, circulate the coolant faster to bring down the temperature problem. So we're going to sense coolant temperature and help control idle speed. Coolant temperature is also obviously going to help us control fuel delivery. We had already said on a very, very cold engine, we're going to pulse the injectors on for a longer period of time. As the engine warms up, we will start to lean out the fuel delivery. Coolant temperature again, and spark timing. We want more spark advance on a cold engine. And as the engine warms up, we will decrease spark timing or decrease advance. Coolant temperature is also an input signal for EGR control. We don't want EGR in a cold engine. It's also an input signal for torque converter clutch control. On a cold engine, we don't want the additional load of a torque converter clutch, so by sensing the coolant temperature, we will control that specific parameter. Engine crank, okay? The engine crank signal, okay, as we saw in the cold start valve, okay, which is a non-ECM controlled device, but that's going to control that particular injector. But on the engine crank on other systems, we're going to use the cranking signal to control the fuel delivery. In other words, if we give the ECM a cranking signal that comes directly from the starting motor, the ECM will now know you're cranking the vehicle, and based on the RPM signals, coolant temperature and throttle position, it'll know how much fuel to deliver to that engine. And if it's a cold engine and it's a cranking RPM, or the cranking signal will say pulse the injectors for a long period of time to deliver the cold enrichment fuel that we need. Detonation. We're going to sense that through a detonation sensor or a knock sensor, and obviously we're going to control the spark timing. And we're going to retard spark based on the engine knock signals that we're getting. We're going to do that with a knock sensor or a piezoelectric crystal, which will generate an AC voltage when it's vibrated or when it's moved. Okay, this vibration sets up the voltage. That signals an electronic spark control module, which signals the ECM to retard the timing. So again, sensing engine detonation will control spark timing. Okay, next down here on the sense parameters is exhaust oxygen. Now, obviously, we're all familiar with that with the closed-loop system because this is the major input signal for closed-loop operation. It is the input signal for closed-loop operation, as a matter of fact. Okay, lean exhaust, rich command, rich exhaust, lean command. Okay, we all know that from the C3 carburetor tape. Okay, we're controlling injectors now, and of course, we are talking about fuel control. If we have a lean exhaust, we're going to turn on or we're going to pulse the injector for a longer period of time to compensate with more fuel. If we have a rich exhaust, we're going to shorten the pulse duration of the injector to lean out the fuel delivery to compensate for that rich condition. Again, closed loop system. And you're going to monitor this on your scan tool in integrator and block learn memory as you did with the throttle body systems. You're also going to use your check engine light in a field service mode to monitor the activity of the oxygen sensor and to determine whether we're in open loop or closed loop and whether the exhaust is rich or lean. Let's go back for a second. In field service mode, when we grounded the diagnostic test terminal with the key on, okay, the check engine light is going to flash, of course, trouble codes. If we start the engine, it's going to flash in the rhythm of the oxygen sensor activity. With the engine running, the check engine light will flash 2.5 times per second to indicate open loop operation. It'll flash once per second to indicate closed loop operation with perfect 50% transitions. 50% above the transition voltage of the oxygen sensor, rich, 50% below the transition voltage of the oxygen sensor, lean. Okay? So closed loop once per second, on and off, to indicate a 14.7 air fuel. If the light is on most of the time, then the engine is running rich, and the oxygen sensor output voltage will be in a high state, above 0.6 volt. If the light is out most of the time, the oxygen sensor voltage will be in a low state, 0.3 volt or below, and the exhaust will be lean. Okay? Let's move down to crankshaft position. We're going to use this, obviously, for spark timing control, either through the pickup coil in our HEI distributor systems, okay, or from the crankshaft sensor that we're using on a particular engine like this. It utilizes a crankshaft sensor in its direct ignition system. Cam position. Cam position is used on sequential fuel injection systems such as this car to start the sequence of injector firing. Again, on a sequential fuel injector car such as this, we're firing the injectors in order, 1, 6, 5, 4, 3, 2, just like we're firing the spark plugs. And because we're firing them one by one, the electronic control module needs a starting point. It'll use the cam sensor to do that. MAP and TPS, manifold absolute pressure sensor, which we're going to use on a speed density port fuel system car, such as like a 1988 V6 Chevrolet Cavalier, where we're using speed density. Okay, obviously we're going to control fuel and spark timing in conjunction with torque converter clutch. Remember, if the engine's under heavy load, we don't want a torque converter clutch, and that load will be processed by the MAP sensor. If we're at wide open throttle, or if we have high MAP, we're going to retard the spark. Okay, if we have high MAP, wide open throttle, we're going to supply additional fuel for that particular mode. And throttle position, the same thing. Torque converter clutch, spark timing, fuel control. Obviously, our fuel requirements are going to require, okay, more fuel based on increased throttle position. Park neutral switch. This is a sense parameter that is going to indicate whether the vehicle is in park or neutral or whether it's in gear. The difference is this: if we're in park or neutral, okay, and the engine's under a no-load situation, we can maintain a lower idle speed. As soon as we shift the vehicle to gear, whether it be reverse or drive or any other forward gear, okay, and we load down the engine, okay, the ECM will get that as a sense parameter to control the idle speed. Obviously, when we drop it down in gear, we're going to increase the idle speed to compensate for the additional load on the engine. We're also going to use the park neutral switch for torque converter clutch application, and in some cases, electronic spark timing as well. Vehicle speed sensor. The vehicle speed sensor, okay, sensing vehicle speed, is going to indicate to the ECM when we should control the torque converter clutch. Typically, at 40 miles an hour, we will turn on the torque converter clutch based on the vehicle speed sensor. The gear status. We have switches in the transmission that tell the ECM whether it's in third gear or whether it's in fourth gear. And these particular sensed parameters will be used to, again, control torque converter clutch application. On some systems, we're going to use the VSS signal to control purging of the canister. Below a certain mile per hour, we will not purge the canister of fuel vapors. Above, say, 15 miles an hour, we will start purging the canister of collected fuel vapors. We'll also use the vehicle speed sensor on particular applications to control the electric cooling fan. If we are generating a speed of 30 miles an hour or greater, the airflow through the radiator is sufficient to cool the engine. So we don't need the additional load of electric cooling fan being turned on. So through the sense parameter of vehicle speed, we can also control the cooling fan. Okay? And the cooling fan is controlled by the ECM through a cooling fan relay. Mass airflow sensor, okay, we've talked about this earlier, sensing directly the airflow through the mass airflow sensor, and the ECM looking up in a table. In other words, set airflow equals set amount of fuel delivery. Okay, we're obviously going to control the fuel control system. We're also going to use the mass airflow sensor signals to control spark timing. Manifold air temperature sensor. Okay, that is going to be what the temperature is of the air coming into the plenum. Manifold air temperature is very critical because it's going to basically dictate or tell the ECM what the charge density is. If we have a specific volume of air that is heated to a certain temperature, its percentage of oxygen will decrease as we increase the temperature. And because it is oxygen, what we burn in the combustion chamber, the higher the temperature of the air, the less oxygen we have to burn. Okay? Conversely, if we have a cold air charge, we have more oxygen and it's more combustible material for these cylinders to fire. So that particular information sensed by the manifold air temperature sensor will tell the ECM how to control spark timing and fuel control. So the manifold air temperature sensor. The EGR is sensed through either an EGR position sensor used on Generation 2 2.8 V6 engines, or through an EGR temperature switch that's used on specifically a 5-liter or 5.7-liter Chevrolet V8. The EGR temperature switch, for example, we can sense the temperature switch, whether it is opened or closed, and the ECM can now know whether the EGR is actually working or not. Okay? Power steering. When we have a power steering pressure switch in the high side of the power steering line, and what this is going to do is help us control idle speed and air conditioner operation. When we turn the wheels all the way to the either extreme, right or left, and power steering pump pressure builds to its maximum, a normally closed set of switch contacts will open, changing a signal voltage at the ECM, which will tell it to turn off the air conditioning compressor, so we don't have a near stall condition. And at the same time, increase or retract the idle air control valve to increase the idle speed. So through a sense parameter of power steering pressure, we can control idle speed and the air conditioner compressor. And by monitoring system voltage back at the ECM, okay, we can control, for example, the electric fuel pump. For example, if the system voltage falls down to a specific level, and we'll say 10 volts, okay, what we can do is we can start pulsing the injectors for a longer period of time, okay, because obviously if we decrease the amount of voltage to the fuel pump, obviously it's going to be turning slower. Obviously, fuel pump pressure will be less than it was if the fuel pump was operating at 14 volts. So what we can do is to compensate for that lower system voltage, we can pulse the injectors for a longer period of time to compensate for a leaner fuel pressure. Okay? We can also increase the dwell time in the ignition system to compensate for decreased coil saturation, which would have occurred if system voltage fell below normal charging system voltage. So basically, you can see how the sense parameters, okay, the ECM picks these sense parameters up through different switches and sensors underneath the hood and will control a variety of systems based on what it's looking at underneath the hood for precise fuel control, precise spark timing control, and again, performance and economy. Why did we cover controlled and sense parameters? Well, let's take two very, very realistic examples of why it's important to know what the ECM is sensing as to what it controls. I had a problem a few weeks ago. A guy called me up and he said the drivability symptom was that the idle speed of the engine was abnormally high and that the air conditioner was not working. Now, typically these don't seem like two related problems, but yet They were both a result of a malfunction in the power steering pressure switch. The power steering pressure switch failed. The ECM thought that the power steering was always locked, either right or left, developing very, very high power steering pressure. And what it normally will do when it senses this parameter is will control idle speed by increasing idle speed and will turn off the air conditioning compressor clutch, because the ECM will control the compressor operation through a AC control relay. Well, the pressure switch failed such that the ECM thought the wheels were always locked. So no matter what happened, the air conditioner compressor would never come on and the idle speed would never come down. Because remember, the ECM didn't know any better. So sense parameter, power steering, okay, control, idle speed and air conditioning, drivability symptom, no air conditioning compressor and high idle speed because of a failed power steering pressure switch. So this is why it's so important to know sense parameters, controlled parameters. Another one, drivability symptom, very, very poor performance, and possibly in an extended condition, an overheating problem due to an overactive knock sensor, or possibly an abnormal underhood noise such as a valve tap or something of this nature. What will happen here is this. When the knock sensor, which piezoelectric crystal, generates a voltage upon vibration, it senses this frequency, okay, and it starts retarding the timing. Well, if you got a valve tap or something of this nature, timing is always going to be retarded, so obviously performance is going to suffer. And we know when we retard the timing, because the burn is being completed later in the power stroke, the coolant temperature is going to rise dramatically. So you could have not only a poor performance problem, but an engine overheating problem, okay? And electrically that could be caused too, again, just by an oversensitive or overactive knock sensor. The knock sensor generates a AC voltage about a peak of 250 millivolts. Okay, again, an oversensitive knock sensor could create some intermittent drivability problems. Again, poor performance because we're retarding the timing. Okay, so these are just two examples of real-world drivability problems based on sensed and controlled parameters. So it's very important to know what one particular sensor is responsible for so you can make a drivability diagnosis. Another example is that if a customer is complaining about detonation, well, we know that there's a million things on today's vehicles that can create spark knock. But if you know that the coolant sensor is responsible for the electronic control module's spark timing, then you know that's one more area to look at for a possibility in spark control or a detonation problem. Don't always rely on a stored trouble code to indicate a malfunction. Sense parameters, controlled parameters, knowing what affects what is going to help you be more precise and more accurate in your diagnosis and more successful. Before we get under the hood, let's review or let's talk about essentially the primary distinction between port fuel and throttle body injection systems. And that distinction would be the mass airflow sensor. Okay? There's a variety of different types, and the one I'm holding in my hand happens to be a AC mass airflow sensor, AC Delco mass airflow sensor. They come in either AC Delco or Bosch. Okay? Basically, what the mass airflow sensor does is directly measures, okay, the airflow through the induction system into the engine. And what it does is the ECM will monitor, okay, the temperature of a thick film if it's an AC type sensor. And what it wants to do is keep the temperature of that grid 75 degrees above the ambient temperature. Now, in order to do that, it's going to have to supply electrical current. The more air that flows across that grid, the cooler the grid becomes. The higher the electrical current will be needed to maintain it at 75 degrees above ambient. That electrical current is going to be measured through the voltage drop back at the ECM, okay, that 5-volt reference signal. That reference signal is going to be translated into a frequency between 30 and 150 hertz. 30 hertz would be a very, very low airflow, basically idle. Wide open throttle would give you a frequency output of about 150 hertz. If you would translate those frequencies into your scan tool, okay, your scan tool is going to read airflow in grams per second. And at idle, the 30 hertz signal would translate into approximately 3 grams to 5 grams per second. And at wide open throttle, that 150 hertz would translate into approximately 150 grams of airflow per second at wide open throttle. Now, the AC Delco type mass airflow sensor has a 3-wire connector to it. Terminal B is the 5-volt reference signal, okay, to the ECM. Terminal C is ground, and terminal A is a 12-volt battery feed through a 20-amp underhood fuse, okay, that goes through a mass airflow sensor relay, which is located somewhere near your radiator support. Now, this specific type sensor is used on 2.8 Chevrolet motors, 3.8 Chevrolet motors, or I'm sorry, 3.8 Buick motors, 3-liter Buick motors. Basically, it's a 3-wire type sensor, okay, that uses again, a mass airflow sensor relay. Speed density versus mass airflow. We remember this from throttle body injection. Our green-coated manifold absolute pressure sensor had a vacuum signal here, told the ECM of engine load conditions, and we calculated airflow through this map sensor signal. Mass airflow sensor, we directly measure airflow, and the ECM will compare it to a lookup table and calculate what the fuel delivery should be. One thing unique about this particular mass airflow sensor, it is of the AC Delco variety. It has 3 pins, though, versus the 3-pin AC Delco mass airflow sensor. The difference is that this particular sensor incorporates a manifold air temperature sensor inside of it. So if you're hunting around for the MAT sensor on a 2.8 V6W motor, don't worry, it's there. It's inside the mass airflow sensor. It's a 5-pin MAP sensor. On other applications, the manifold air temperature sensor, which you see here, which is a thermistor, works just like the coolant sensor, is located in the intake plenum or the air cleaner assembly, wherever the air induction is. So it can pick up the temperature of the air and tell the ECM of charge density. Now, on the 5-liter and 5.7-liter Chevrolet motors, they use a Bosch hot wire type mass airflow sensor. And basically, the theory is the same. They want to keep the temperature of the hot wire 75 degrees above ambient, and the voltage drop, okay, as a reference as far as what airflow is. In other words, the more electrical current we need to maintain that temperature, the greater the voltage drop will be, and that will dictate what the airflow is. Now, one difference between the hot wire Bosch and the AC Delco type mass airflow sensor is because we're using a hot wire here, due to contaminants in the atmosphere, they will ultimately collect on the hot wire. So these particular applications use a burn-off system or a burn-off cycle. Whenever the vehicle is turned off in closed loop, after a 3 to 4 second delay, the ECM will apply voltage to this hot wire. It'll glow red for approximately 1 to 2 seconds to approximately 1,000 degrees Fahrenheit, and that will burn off any residue off the hot wire. So you could actually make this test right in the stall by simply disconnecting the ductwork and hanging the mass airflow sensor loosely. So you could look at it. This is especially easy on a Corvette or a Camaro, where the induction system is very easy to work with. The Trans Am's a little more difficult the way it goes off to the right angle. But if you would hang the sensor with it plugged in loosely so you can look into it, if the vehicle is in closed loop, okay, that means the serial data line, terminal E of the ALCL, will be in a low voltage state, approximately 2.5 volts or lower. It is this voltage on the serial data line what triggers the burn-off circuitry. When that voltage drops 2.5 or less, when the ignition is cycled off, the ECM will wait 3 to 4 seconds and then apply voltage on this hot wire. Now you can see that. As soon as you turn the key off, wait 3 seconds and you will see it clear as day that wire will glow orange, a very, very bright orange as it glows and burns off that residue. This is the way you can check burn-off. Now, a quicker way to even do it is rather than wait till the vehicle goes to closed loop and then shut it off, you could take a jumper wire from terminal E of the ALCL and jump that to ground. And this will keep the data line in a very low state, 0 volts. When you turn the engine off, it'll automatically, okay, the ECM will automatically think you're in closed loop, even though you're really not, and it'll trigger the burn-off circuitry. Then you can look in your mass airflow sensor and see after a 3 to 4 second delay if the hot wire is glowing. And if it is, you know the system's working properly. In 1986, they incorporated a fault code 36 to detect a fault in the mass airflow burn-off circuit. In 1985, the burn-off circuit was controlled through a separate module that was bolted to the ECM. In 1986, they did away with the module and went to a mass airflow sensor burn-off relay and a mass airflow sensor power relay located on the left portion of the firewall underneath the hood. The fundamental circuits operates the same way. They just use some different components to do it. So that test will be valid on either an 85 or 6 or later model. Okay, I want to take a look at a code 46, which is solely applicable to a 1986 Corvette, 1987, and 1988 Corvette. This has used the vehicle anti-theft control system. Okay? Now, how does this tie in with poor fuel injection? Well, you can get a no-start complaint, and it could be a function or a malfunction, excuse me, of the vehicle anti-theft system. The vehicle anti-theft system incorporates what they call a VATS decoder module. What this module is responsible for is determining what the resistance of the special key pellet is in the ignition key. Each Corvette's got a little copper pellet or a brass pellet in its ignition key, which has a specific resistance value. That resistance value is read when the key is inserted into the ignition switch through the VATS decoder module. If the decoder module, which is supposed to be matched to the ignition pellet, if it senses that the right key is being used, okay, two inputs will occur. It will ground the starter enable relay so you can now crank the motor, and it will also ground terminal B6 of the ECM, pulling the 5 volts down to 0 volts. That's the cranking fuel enable signal, okay? Now, if the wrong key is inserted, the VATS decoder module will not pull these circuits to ground, the ECM will not get the right signal, and it'll set a code 46. What will happen is, again, as soon as the key is inserted and you turn the ignition switch on, there's an ignition input to the VATS decoder on terminal S. It expects to see the proper matched signal from the decoder to the ignition. If it doesn't see that, the ECM will not get the 0 volt signal that should be supplied by the VATS pulling this circuit to ground. The lack of that correct signal will trigger a code 46. And again, this can create a no-start condition. In many cases, you can get a no-crank condition if there's a malfunction in the VATS decoder module or the ignition switch. So keep that in mind with Corvettes 86 and up in diagnosing a no-start or a possible no-crank condition. Let's look at some of the components that make up the vehicle anti-theft system in the Corvette that we talked about could create a no-start condition. We have the special ignition key with the resistor pellet. This is the vehicle anti-theft system decoder module, and the key and the decoder module are a matched set. And this is your special ignition key cylinder, which has the contacts inside that touch the resistor pellet. This is your starter enable relay. And of course, we talked about ultimately that this system will not pulse the injectors if the wrong key is inserted. When you have to clear the ECM long-term memory, against the firewall you'll find a gray connector, and it's got an orange wire coming to it. That is your random access memory feed line. To clear the ECM memory, simply disconnect it for 10 seconds and then reconnect it. Okay, let's look at some fuel system diagnosis with the fuel pressure gauge. And by the way, your fuel pressure gauge is one of the most important tools that you need to diagnose a fuel injection system. You're going to connect your fuel pressure gauge to the fuel pressure tap on your rail, hang it somewhere convenient underneath the hood, and your gauge should be calibrated from 0 to 100 psi. It's also calibrated in kPa or kilopascals, and to make the conversion, kilopascals to pounds per square inch, 6.9 kilopascals equals 1 psi. So you'll notice at 100 psi, you've got 690 kilopascals. Many fuel pressure specs will be given to you in kilopascals, so you know it's made the conversion. Now, we've already diagnosed or we've already qualified the integrity of the fuel pump relay electrical circuit when we did our little test with the test light and the test connector. Now, this is a non-Chevrolet, and we could use that test with the test light. We can also use it to prime the fuel system. I've got a jumper wire hooked up here. When I apply 12 volts, we will turn on the fuel pump, and we should instantly build up fuel pressure. So let's see what happens when I connect the fuel pump test connector to 12 volts. Okay, fuel rail pressure has developed or built up to 42 pounds per square inch, which is fine. It's very good. Now, what we want to do now, we know we've built up sufficient pressure. Now we want to see if the pressure is going to hold. But let me step back for 1 second. With the engine off, the fuel pressure regulator is closed, so we should build up maximum fuel pressure, the same fuel pressure we'd build up if the engine was in wide open throttle conditions. So you can see 42 psi foots the bill. Okay, there's no problem there. Now the second thing we want to notice, if we didn't have proper fuel pressure here, we possibly have a clogged fuel filter, whether it be an inlet fuel filter in the tank or an inline fuel filter in our feed line. Okay, that can create low fuel pressure. Okay, if those systems or if those filters are good and we still have low fuel pressure, we've possibly got a defective fuel pump. So you want to make the determination by going to your filters first, and then you possibly have a bad fuel pump, as long as there's no clogs or restriction or kinked fuel feed lines. We've got good fuel pressure here. Now the second thing we're looking for is, will fuel pressure hold steady? And it should. When we shut the vehicle off, if we maintain fuel rail pressure, it makes for very, very quick restarts. But if the fuel pressure bleeds back down to the tank, now we've got to repressurize the rail for the next restart. So we want to make sure that it maintains rail pressure. Now, as you can see in this vehicle, it is holding at a steady 42, and it's been that way for the length of time I've been speaking. Now, let's assume for 1 minute that fuel rail pressure built up to 42, but once it peaked at 42, it started to drop. Okay, now what you're going to want to do is isolate where the fuel bleed back is occurring at. Okay, so assuming the fuel pressure is dropping here, okay, first thing we're going to do is clamp off the fuel feed line to see if the pressure continues to drop or whether it stops dropping. If the pressure is dropping and I clamp off the feed line and the pressure now holds steady, then I've just isolated the bleed back problem to the check valve in the fuel pump. Okay? So if the bleed back stops when I clamp off the feed line, you've got a problem in the fuel pump check valve. Okay, as we move on. Okay, I clamp off the feed line and it's still bleeding down. I still got a problem somewhere. So now if I clamp off the fuel return line, okay, and it continues to bleed back, or I'm sorry, if it stops bleeding back, we know we've got a problem in the fuel pressure regulator. So if we clamp off the feed line, or I'm sorry, the return line, and fuel pressure now stabilizes and stops bleeding down, we know we've got a problem in the fuel pressure regulator. Because now what we're essentially doing is we're clamping off the inlet, we're clamping off the outlet. So now the fuel's got nowhere to go. So if fuel pressure now stabilizes, we know we have a problem on the regulator side. Okay? Well, let's say now that we've done that and we still have fuel pressure bleeding down. We've clamped off the feed line, we've clamped off the return line to isolate check valve and regulator, and yet the fuel pressure is still bleeding down. Okay, more than likely we have a leaking fuel injector. If the injector doesn't close properly when the car is shut off, fuel will continue to drip into the cylinder. And what will happen is this will make restarts either very, very difficult or almost impossible as the spark plug gets saturated with fuel. So your fuel pressure gauge is going to help you determine what possible problems you may have, whether it be a long cranking problem, a rich running problem, or a no start condition. By isolating the particular circuit in the system, whether it be the feed line, return line, or injectors, you will determine where the specific problem is. And isolation of this problem is critical. Okay, you can't guess at this. You've got to be able to isolate the particular area the problem's occurring in. And by isolating the feed and return lines and injectors, you can do this very, very quickly. Now, if you've isolated it down to an injector that is sticking open, okay, what I have done is usually I will take the fuel injector rail off, okay, with the feed and return lines still connected. and I'll hang it somewhere conveniently under the hood, because these are connected to flex lines, okay, and you can take the rail off from the plenum and hang it somewhere. Now, if you pressurize the system, you will actually see what injectors are leaking, as you will see the fuel dribbling out of the leaking injectors. These injectors would have to be replaced to correct the bleed back problem. Okay, we've looked at fuel system diagnosis, and on that line, I want to do some injector testing. And what we're going to do specifically is an injector balance test. And this is similar to a compression test that we do on cylinders. We're not looking for exact readings. We're looking for consistency of readings. For example, we take 120 pounds from one cylinder. We want to see all the other cylinders within 10 to 15 pounds of that particular cylinder. Relative compression, it was called. Well, we're going to do an injector balance test. And basically what we want to record is the pressure drop of each injector. Now, there's some equipment that is made specifically for doing this. And this particular tester, you would hook this up to the battery. Okay, these two leads are positive and negative. And then your other lead, you'll hook up to your port fuel injector, if it's a multi-port fuel injector, or it's got two leads here to hook it up to a TBI injector, or throttle body injector. Now, when it's hooked up and you press this button, the red light will glow, and it'll pulse the injector for just a few milliseconds. And then you would read the pressure drop on your fuel gauge, and this way you would do a relative injector test, if you will, and each injector should drop about 3 to 4 psi as it's energized. Now, the injectors that drop more than that, okay, these could be your leaking injectors that you may have found in your fuel systems diagnosis, okay? These could be the injectors causing your code 45 or rich exhaust condition, okay? These could be the injectors causing your black smoke possible rich problem. Now, when you pulse the tester and your injector drops very, very little or not at all, these are the injectors that are causing your lean running condition, poor performance problem, okay? Maybe they're filled with dirt. Maybe when the injector opens, there's so much dirt around the seat that even though it's spraying some fuel, it's spraying much less fuel than it would if it's dirty. So this is another way to determine if the injectors need a good cleaning or not. Now, there's two types of port fuel injectors. Besides the manufacturers, Bosch makes injectors for General Motors, and Rochester has just recently started making injectors for General Motors under the Multec name. Now, the way you can determine if it's a Multec injector or not is if it's got a silver ring around it. This will classify it as a Rochester Multec injector. These injectors were started in 1986, 87, and they're using them now. Okay, the test is done exactly the same. The Bosch injectors on the early systems were very prone to plugging and leaking as well, so I guess that's why they went to the Rochester design. Now, there's also two distinctions you need to make in injectors, port fuel injectors. Some are low impedance injectors and some are high impedance. Low impedance, which means it's got a very, very low resistance value. The resistance value on low impedance injectors is 2.5 ohms or less. Now, why is the impedance important? Well, if you don't have this kind of equipment to do an injector balance test, you could do that, you could energize that injector by applying a voltage source. If you've got low impedance injectors, however, and you hook it up to a 12-volt source, you'll instantly burn out that injector because it's going to draw too much current. So to pulse those injectors, you would use a flashlight battery or 2 flashlight batteries. And anything under 5 volts DC will keep the low impedance injectors from burning out. Now, those low impedance injectors are found on the 4-cylinder fuel injected systems of General Motors, specifically the 1.8 liter turbo, the 2 liter turbo, both Pontiac motors, and the 2.3 Oldsmobile Quad 4, which is a multi-port fuel injection system. All these systems use low impedance injectors. So if you don't have this particular equipment to do a balance test, again, use flashlight batteries, anything less than 5 volts to turn these injectors on. If it's a high impedance injector, which is found on all the V6 and V8 applications, you could apply 12 volts for a very short period of time to the injector to turn it on. Now, again, to determine, in case you're not aware of what is low and what is high impedance injectors, just hook up your ohm meter to the injector and put it on the low scale, and you can read. The low impedance injectors will be less than 2.5 ohms, maximum at 2.5 ohms. Your high impedance injectors will be between 12 and 16 ohms. And as you can see here, I've got the ohm meter hooked up to one of the injectors on this car, and it's reading 14.6 ohms. This is a high impedance injector, so in case you didn't have this particular equipment, for a very short period of time, you could apply 12 volts to open that injector. Okay, after we've done our fuel system diagnosis, what's a real good idea, especially before you do a tune-up on these cars, is to do a fuel injector balance test to see if the injectors are all firing equally. It's pretty much like doing a relative compression test on an engine. We want to see relative compression, the equivalent to 10 to 15 psi within each cylinder. The injector balance test is very, very similar. We want to see what the pressure drop is across each injector as we open it. And they should all be within a few psi of each other. Typical pressure drops when we fire the injector is 2 to 3 psi. Now, if you have one injector that drops 10 psi, then you know that injector is sticking open, and that's probably the injector that's leaking when you do your fuel system diagnosis and you detect a bleed back condition. Well, there's probably your injector that is bleeding back because it's leaking into the cylinder. Conversely, if we have an injector that only drops a half or 1 psi, that injector is probably clogged with dirt. So when the pintle does open, obviously the spray pattern is adversely affected, and the pressure drop is much less than it would be if it was clean. So this is a tip-off. Before you tune that car up, you want to service those injectors, because the best tune-up in the world is not going to take care of a clogged injector. Clogged injector means a lean cylinder. And really, you can do an injector balance test if you don't have this equipment very quickly by pulling one injector plug off at a time and watching the RPM drop, because really you're canceling the fuel to that cylinder and you're doing a mechanical cylinder balance test. So that's a quick way to do it if you don't have the equipment. Okay, so what we're going to do, the first thing we're going to do is disconnect the fuel injector. And because this is an SFI application, sequential fuel injection, remember the injector connector has to go to that particular injector. On double fire MPFI, we could mix up the injector connectors and it wouldn't matter. The ECM fires them all at the same time. On sequential, however, they're fired one by one in spark plug firing order. Consequently, they must be hooked up to the proper injector. Now, this SFI system, the injector connectors are marked as to what cylinder or what injector they go to, so you can't mix them up. You're going to take the plug off your tool and put it right on the injector that you wish to test. You're going to have your injector canceller hooked up to your battery, and you're going to be looking at your pressure gauge. Now, if the gauge is reading, say, 42 psi, you're going to cancel the injector and you're going to notate the pressure drop. Okay? So I'm going to cancel the injector, and we watch my pressure gauge drop. Okay? We're going to record the drop. It was about 4 psi. We're going to record that drop and compare each injector to that initial one. They should all be within, say, 2 psi of each other. And in this way, you can determine what are dirty injectors or injectors that are sticking open or whatever the case may be. A real good idea to do an injector balance test before any tune-up on these vehicles. On this injector balance test, I want to stress this again, why it's so important. When a customer rolls into your shop and the engine is idling rough, or it's performing badly, or it's got a flat spot on hesitation, whatever the case may be, the customer's fix all the time is, my car needs a tune-up. Now, we both know that in most cases, especially today with the electronic controls, that's not the case. Again, an injector balance test is a good prelude to a tune-up if the car actually does need a tune-up. But an injector that's sticking or leaking, again, can create severe drivability problems. From the performance end, if we have injectors that are sticking or are dirty or plugged or whatever the case may be, again, we cannot deliver sufficient supply of fuel to that particular cylinder. So the injector balance test is like our X-ray eyes into seeing what's happening in that combustion chamber. Remember, a throttle body system, we can look at the injector. We can actually look at the spray pattern, especially if we freeze it with a strobe light. Here, we can't see anything. So an injector balance test is really good. It's like X-ray eyes into seeing how that injector is operating. Because again, the tune-up is not the cure-all for poor performance problems. And in many cases, a tune-up is very unnecessary. And you're going to come out smelling like a rose if you tell the guy, hey, sir, you didn't need a tune-up. You just had a couple plugged injectors. We did an injector balance test, then we did an injection cleaning service. Now the car runs like a top. You didn't need a tune-up. You're a hero, okay? And now when that guy does need a tune-up, he's going to come back to you anyway. So an injector balance test, real good to see what drivability problems actually do exist. One of the important adjustments that you're going to have to be familiar with on the port fuel cars are minimum idle air adjustments. Now, this adjustment, according to General Motors, shouldn't have to be done unless the throttle body is disassembled for some reason. But one of the problems that they're encountering with these throttle bodies is that because the blow-by tube or your crankcase breather tube is connected in front of the throttle body, okay, or if the throttle body was turned right side up, it'd be on top of the throttle plate, there's no crankcase filter in there. So what happens is all the blow-by gases are deposited ultimately on top of the throttle plate. And these blow-by gases form a residue that builds itself as sludge around the throttle plate. After a period of time, this residue will restrict airflow and in extreme cases will cause near or stall conditions every time you come to an idle. So it's going to be very important to periodically take your mass airflow sensor duct hose off and remove your mass airflow sensor and clean the throttle plates with some carburetor cleaner. Clean them very thoroughly, open it up and spray it in there real good. And then what I usually do is I'll start the engine up, okay, with the mass airflow sensor disconnected and just let the vacuum of the engine actually suck up any additional residue that's there and it'll thoroughly clean the throttle plate. Now you're ready to check and adjust, if necessary, your minimum idle air rate. How you're going to do this is as follows. You're going to turn your key on and you're going to ground your diagnostic test terminal, or if you're using your scan tool, you're going to put the scan tool in the field service mode. What this is going to do is it will seat the idle air control valve. It'll seat the pintle into the air bypass channel. Now wait 30 seconds and disconnect the idle air control valve while you're still in the field service mode. And by the way, your cooling fan will run continuously while you're in the field service mode. So after 30 seconds, you disconnect your idle air control valve. Now, it is fully seated in the idle air bypass channel, so there can be no air bypass. Now, you've already cleaned your throttle plates. If the vehicle is hard to start or won't start at all, it's a very good bet that your minimum idle air rate is set too low, because that means the throttle plates are not open enough to permit airflow to even start the vehicle. So what you're going to have to do is you're going to have to turn the adjustment screw located on your throttle plate, very similar to the curb idle screw that would be on a carburetor. You just locate your accelerator lever and it's right there. Now, what you're going to do is you're going to turn that screw to achieve whatever the minimum idle air RPM spec would be. For example, if it was a 5-liter Chevrolet TPI, it might call for 550 RPM in drive for your minimum idle air. Now, always read your manuals because there's not only different specs, in some cases there are different ways of setting this. For example, in 1985, Chevrolet wanted you to adjust the minimum idle air by doing exactly what I said, placing the vehicle in gear and adjusting that minimum screw to 550 in gear. In 1986, what they asked you to do was seat the IAC in field service mode, just like we talked about. Now, start the vehicle up and disconnect the set timing connector to put the vehicle in bypass mode timing, meaning it retards the timing to base. Obviously, the RPMs are going to be less. And set your minimal idle air at whatever the spec may be under those conditions. Now, if this is a 1986 vehicle and you didn't put it in bypass mode, obviously your minimum idle air rate is going to be incorrect because you didn't bring the vehicle back to base idle. So the point here is always read the specifications and the procedure for minimum idle air rate for the particular vehicle you're working on. What I've given you is very basic what you're going to be doing. These are your idle air control valves. Two components, different physical appearance. They both do the same thing. This one on my left is out of a 5-liter TPI Chevrolet, and you can see it is got a collar. There's two types of these. There's collars and collarless. Now, what this is going to do is help you install this valve, and I'll tell you why. If it's got a collar, as this one does, okay, before you install it in the throttle body, you're going to have to retract this pintle to within 28 millimeters from the base of the flange, meaning that between here and here, it should not exceed 28 millimeters for installation. On a collar type IAC valve, to retract the pintle, you're going to grab the pintle like this and go side to side as you push it in. That'll retract the pintle on a collar type IAC. If there is no collar here, and you can see the stepped portion indicating a collar, if it's collarless and it's just a smooth connector here, then what you're going to do to retract the pintle is simply turn it clockwise while depressing it, and that'll retract it to your 28 millimeter specification. The IAC on my right is out of this 1988 Pontiac Bonneville. It is a dual taper design. You can see one taper, another taper. It's a dual taper design. This does not use a gasket as this IAC on my left does. It uses an O-ring right here, and you can see it's got the micro pack connectors right in there. Typical resistance values between the IAC coils is between 25 and 50 ohms. Any IAC that would measure under 20 ohms between its coils would be a bad IAC, and also it would damage the ECM because a low impedance IAC would draw too much current into the ECM. After you've cleaned the throttle plates, adjust the minimum idle air rate, what you're going to have to do is check your throttle position sensor output voltage and adjust if necessary. And the typical TPS voltage at idle on your port fuel cars is between 500 millivolts and 550 millivolts, which is half of a volt to 0.55 volts. So you're going to set your TPS, and that would complete the minimum idle air rate procedure. Now, if we look down here at the scan tool, what we can do is, very simply, is program the scan tool to put the vehicle in a field service mode, and this will seat our idle air control valve and also turn our cooling fan on. You heard the cooling fan come on. The idle air control valve is being seated as we speak. Wait approximately 30 seconds and disconnect it. That'll seat it all the way in the bore. And now, again, you can follow the rest of your procedure for minimum idle air rate. If I switch this over to throttle position output, I can now read my throttle position sensor voltage right on my scan tool. This particular piece of equipment flashes between RPM and TPS voltage 1 per second. I got 0 RPM because the engine's not running, and my TPS is 0.42. So you would adjust your TPS accordingly after you've adjusted minimum idle air rate, and that would conclude the procedure for minimum idle air settings. Okay, let's talk about a couple no-start situations that you may encounter. And again, using your scan tool, let's say we have a customer complaining about no-start condition, and of course we know there's a lot of things that can cause a no-start. I'm going to zero in on one specific thing that you may encounter. The ECM operates the system in a clear flood mode. Clear flood, as we talked about a little bit earlier in the program, is a condition where we are cranking RPM and the TPS angle is 85% or greater. Now, with a TPS that high, under a specific RPM, the ECM will go to a cranking clear flood air-fuel ratio, which is about 20 to 1. Well, if you have a problem in the TPS circuit and the TPS output voltage is, say, 4+ volts, 5 volts being wide open throttle, the ECM could be stuck in a clear flood mode. And now, when the customer goes to start the car, it's pulsing the injector so lean that the vehicle won't start. So what you want to do now, of course, is check your TPS output voltage on your scan tool. Be one of the first things you could check after some basics. Does the vehicle crank and whatnot? But look at your TPS voltage. Again, if it's too high, like 4+ volts, it could be stuck in a clear flood mode, preventing the vehicle from starting. Another case that we could get into is no spark, okay, not only equals no firing the spark plugs, but if we're not getting a tack signal, we're not pulsing the injectors either. So what we can do is very simply is plug a Noid light, is what they call, into the injector connector, and while cranking the engine, see if the light blinks. This will tell you that the ECM is receiving an RPM signal and pulsing the injector accordingly. If the light does not blink, you'd want to check for two things. First of all, are you getting an ignition signal to the injector? Do you have 12 volts to the injector? If you've got 12 volts to the injector, it's the ECM's responsibility to complete that circuit to ground. So if the light is not blinking, you possibly have an open wire between the injector and the ECM, or possibly a faulty ECM connector or a bad ECM. As technology moves on, so does downsizing parts. Here we see a PROM, ECM PROM, and this is the ECM cowpack. Right here is an electronic spark control module. All these components now are downsized to fit in this component right here, which is called a MEMCAL, a memory calibration unit. So this small piece here contains all these three pieces here. These three pieces here were used up to 1985, and in 1986 they went to MEMCAL in all port fuel injection systems. Another problem that I run into was an intermittent no-start condition, and the problem was a loose connection back at the fuel pump, back at your fuel tank. You have either a 3 or 4 prong connector back there, and in this particular instance, the latch wasn't secure. And depending on the position of that connector and depending on the road conditions and whatnot, that connector would work its way loose, and of course the fuel pump wouldn't run and you get a no start. When you turn the key on, you can almost hear the fuel pump run. You should be able to hear the fuel pump run. If you do not hear it run when you turn the key on, again, what you want to do is check that fuel pump relay with your test light like we showed you a little earlier. This is basically the components that comprise your fuel pump electrical system. This is a typical fuel pump relay that is typically located on the outer firewall. And this is your oil pressure switch, which is really a fuel pump switch. Another thing we want to look for is water in the fuel or alcohol in the fuel. If we have fuel contaminated with water, the vehicle will run lean. And in severe cases of water in the fuel, you'll get a code 44 and a check engine light for a lean exhaust indication. And obviously, you'll get some poor performance complaints. Alcohol in the fuel can actually short out the fuel pump. If you run into a car with a bad fuel pump because it's shorted out, you might want to take a fuel sample. And how to do that is to see if there's alcohol in the fuel. Get a graduated beaker and fill it with a measured amount of water. Now, to that measured amount of water, add a sample of the fuel from this particular vehicle. Shake it up a good bit. Now, alcohol is attracted to water. If there is alcohol in this fuel, it will raise the water level greater than what you initially took. And this will be a tip-off that there is alcohol in the fuel, and this is what caused your fuel pump to fail. So before you put a new fuel pump in and, burn that one out, you might want to flush that system out and get some fresh fuel in there. So a couple more things about no starts. Let's talk about a no start where engine cranks fine, won't kick over. Don't eliminate that EGR as a possibility. If your EGR valve is stuck open, the inert recycled exhaust gas will dilute the air-fuel mixture to a point where the engine will not fire. And what will happen is, in most cases, because you'll have the inert recycled exhaust gas, it will actually cause the fuel to condense in the combustion chamber, wetting the spark plug. So you'll typically come away with a problem with fouled spark plugs. But don't always look for leaking injectors to be the cause, because, again, a stuck open EGR valve will cause this condition. It will cause fuel to condense and wet itself right on the spark plugs, causing a no start. An idle air control valve could give you a no start, especially in cold weather. In cold weather, based on the coolant temperature sensor signal, the ECM is programmed when we turn that key on, to retract the IAC valve to provide a good startup idle, just like a fast idle or a choke on a carbureted car. If the IAC valve obviously isn't working and it's all the way extended into its bore, we don't have enough air bypass to keep the vehicle idling fast enough to give us a good cold start. So this is another thing you might want to look at. On your scan tool, the IAC, like we said earlier, is brought down to steps, 0 to 255, 0 meaning fully extended, 255 meaning fully retracted. To test the system, what we can do is with our scan tool plugged in and the engine running, monitoring our IAC steps, turn on the air conditioning and see if the scan tool has recorded an additional number of steps as the ECM now retracts the IAC for an up idle. Now, in addition to that, look at your RPM signal and make sure the RPM of the engine has increased a little bit. Because remember something, and a common mistake some fellows make is that they rely on a scan tool for a complete picture of things that are working, and it's not always true. The scan tool is going to give you an indication of what's happening electronically. Is the ECM sending a proper signal, or is it receiving proper information? It is not always a true picture of what's actually happening mechanically. So even though you're recording the steps of the IAC, perhaps it mechanically isn't functioning properly. Now, let's say, for example, you've got that starting problem where the IAC is fully extended, hard to start. Pull a vacuum hose off, give it a little more air, and it may start up a little easier, especially if it's a speed density system, as we talked about a little earlier. So these are a couple more little things that you'll want to look at. Again, don't always rely on a scan tool as making mechanical diagnosis, okay? Look at the component itself, to verify whether it's mechanically working or not. One more thing about the fuel pump relay. A bad fuel pump relay will not cause a no start. I want to make that clear because remember, we are running in series with that fuel pump relay an oil pressure switch, which is a redundant component that in case of a fuel pump relay failure will continue to run the fuel pump based on at least 5 psi of fuel pressure. A bad fuel pump relay, the drivability symptom will be simply this: extended cranking time. So the customer says, hey, the car used to always start up within a few seconds. Now it takes 15 seconds before it starts up. Okay, that's a real good tip-off to a bad fuel pump relay. And again, you want to test it with terminal G if it's a non-Chevrolet, or the fuel pump test connector out underneath the hood. And check it for a test light lit for 2 seconds to see if the relay is working. And if you don't have a test light or you want to make a quick test, when you turn the key on, listen and see if you hear the fuel pump running. If you do, you know the fuel pump relay is working. Just a couple things on the mass airflow sensor. We can use a scan tool to see what the grams per second of airflow is. Now, on most scan tools, there'll be 2 positions for that airflow measurement. One will say airflow, and one will say maybe load filtered variable or mass airflow, depending on the manufacturer's product. Now, if there's a malfunction in this system and the check engine light has come on and there's a 33 or 34, the mass airflow reading on your scan tool will be the default value that the ECM substitutes if there's a malfunction. If you look at the airflow value on your scan tool, if there's a trouble code, that value will be the last recognized airflow when the fault began. So you'll have 2 different airflow measurements under those conditions of a 33 or a 34. Under normal conditions, both scan tool positions would read exactly the same. At a low throttle position or an idle condition, you'd read low grams per second, maybe 3-4 grams per second, and at wide open throttle, of course, that should increase as throttle position increases. There are some tools on the market that are marketed as mass airflow sensor tools. I've used some in the dealership level with limited success, okay? So basically, one more thing about the mass airflow sensor. If you have a car that is a no start and you've eliminated other things for no starts, unplug the mass airflow sensor. If the car starts, okay, you have a defective mass airflow sensor. The ECM has substituted the default value to start the vehicle. So this is another way you might be able to diagnose a mass airflow sensor. As always, I thank you for choosing a PEG videotape program. Now, this port fuel injection tape in conjunction with the electronic fuel injection tape that you previously viewed should give you a real good background now on the General Motors electronic port fuel injection systems. And I hope you can go out there now and feel real comfortable diagnosing these systems and make some money, because, hey, that's the bottom line, as I've said before. As for me, I'm going to close the hood on this one, and I'm out of here. Take it easy.